Pier thickness influence for turbulent water flow using particle image velocimetry. Abstract: the obstruction of water flow by structural elements such as the bridge pier generates turbulence, which fosters the phenomenon of local scour, especially during rain seasons over extraordinary avenues, and sediment drag presence is bigger. The non-destructive full-field optical technique, commonly called particle image velocimetry, has been a resource of great importance in providing a better understanding of fluid movement, in which data about its turbulence is obtained. With this technology, within a hydraulic scale channel, it was possible to observe the water flow that passed through a circular pier, using 3 thicknesses, obtaining images of its behavior and figuring a nomogram about turbulence distance. Keywords: thickness, pier, flow, scour, particles, image, velocimetry. Introduction. Particle image velocimetry, PIV, since the early 1986, is an optical non-destructive full-field technique. It has been used as a resource of great importance to study the behavior of water movement over surfaces. With the PIV and software for image processing, data movement of water has been obtained from vectors in turbulence locations that are generated at the bottom of a channel by obstruction structures such as bridge piers. Figure 1, it is shown PIV equipment and hydraulic channel. No hay description de la photo disb1able. Figure 1. PIV equipment and hydraulic channel. Since computers and cameras with CCD technology, charge-coupled device, were developed, it laid the foundations of this digital technology too, giving rise to high-resolution imaging 7, which is intended to deepen the understanding of the phenomenon of scour, characterizing the flow speed, its hydrodynamics, linear patterns, vorticity, and shear stress 3, 5. It is also possible to analyze the size of the sediment transportation and the depth of scour that can be generated around structures such as a bridge pier. 14. Pier scour. The formation of pits around the bridge pier over a river or channel is almost inevitable, generating scour that reduces the bottom bed due to a high level of turbulence and vorticity. 9. The presence of foundations on the river bed should be avoided as much as possible. 10. And, if necessary, be as slender as possible in order to avoid its obstruction as much as possible. 11. Nowadays, results are not completely satisfactory to face the problem of scour, so studies such as the placement of sensors could help to understand in greater detail the water flow behavior, which generates the removal of sediments around the foundation of bridges, piers and abutments. These same studies are used to verify the structural quality of the bridge using vibration methods 4, which is expected to improve the available deterministic stochastic or empirical mathematical models. It is hoped the combination of many studies will lead to laboratory results that are more attached to the real system, and that numerical models, whether simple or very complex, that are used to characterize sediment erosion, offer better understanding of scour in the future. 12. With this, scour problems in the pier of a bridge such as shown in Figure 2, could be foreseen coming from the original design, or resolved after being evidenced in existing infrastructure. La imagen puede contener, exterior y agua. Figure 2. Light scour on a bridge pier after raining. Methods. A video of the water flow in a 0.50 m long, 0.15 m deep and 0.15 m width, hydraulic channel with a 1.5 HP electric pump, was captured in the laboratory using a CCD camera previously calibrated, in order to characterize the movement when obstructed by 3 thickness scale circular pier model. Tracer and reflective 9-13 m particles inside water were used for illumination by a 532 nanometer green laser 13. Subsequently, the video was loaded and processed using a visualization software, in order to extract data from it. PIV is based on the study of speed through mathematical expression, v equals d/t, where d is the distance traveled by a particle at a given time t. That's why v is the speed acquired by the particles when taking the trajectories of the flow. The displacement is obtained using a Gaussian function at the peak of the correlation, and finding the exact maximum location. 8. Figure 3, it is shown a CCD camera, laser, and hydraulic channel laser illuminated. Figure 4, Additional photos are shown for CCD camera and 532 nanometer green laser equipment. No hay description de la photo disb1able. Figure 3. CCD camera, laser equipment, and hydraulic channel. No hay description de la photo disb1able. No hay description de la photo disb1able. Figure 4. CCD camera and 532 nanometer green laser equipment. For this experiment, subsequently a water 0.09 m flow level was applied with particles seeded and illuminated by the laser beam, with a speed of 0.0084 m/s, equivalent to a flow rate of 0.107253 l/s, for upstream area, observing downflow position, with the Reynolds number, Re, equals 235.87, then it was decided to increase speed for turbulence appreciation up to 0.117 m/s, equivalent to a flow rate of 1.577 l/s, with the Reynolds number, Re, equals 3289 and 0.163 m/s, equivalent to a flow rate of 2.22 l/s, with the Reynolds number, Re, equals 4573 for downstream area, creating a vorticity distance nomogram. 500 equals Re equals 2000, equals, slash, where, equals water density, equals water speed, equals hydraulic radius and equals water dynamic viscosity. In Figure 3 it is shown this experiment with the laser lit particles, and Figure 5, it is shown the location of the upstream and downstream areas. Figure 5. Location of the upstream and downstream areas is shown. Finally, the video was recorded with a CCD camera, taking 40 images of 24x24 pixels at 700 microseconds. The videos were processed by Lavizion Davis 8 software, from which data were obtained in DAT system format. The files in DAT system format were post-processed by the TechPlot 360 software to obtain images, which final result was the average of the 40 of them formed in video. It is shown Figure 6, Pier model and illuminated flow particles with Pier by laser. It is shown in Figure 7, Pier model and high-speed downflow illustration at upstream location area arrowed by red line. No hay description de la photo disb1able. Figure 6. Model Pier and illuminated flow particles with Pier by laser. Figure 7. Pier model and high-speed downflow illustration at upstream location area. Results. In Figures 8, 9, and 10, at 0.0084 m/s for upstream section, the obstructed water flow behavior was shown by circular scale Pier model, using 10, 20 and 30 mm thicknesses. Vortex was appreciated at different positions due to the Pier's thickness, going further back water downflow and upper. Hence, for downstream the turbulence was bigger, from slender Pier to thicker Pier, until hitting against it. Arrowed line leads each horizontal and vertical distance from vortex to Pier, indicating their position. It is shown in TABLE1, downflow vortex and its position due to Pier thickness. 500 equals Re equals 2000. Pier. Speed. Table 1. Vortex position in X and Y axis. It is shown in Figure 11, the three vortex positions at the same time due to the Pier obstruction, using a blue circle for the slimmer one and gray polygon for thicker one. Figure 11. Three vortex positions at the same time due to the Pier obstruction. In Figure 12, it can be seen the percentage of distance downflow vortex relation, from each other from Pier upstream area. The blue color represents 10 mm Pier with 27%, red color represents 20 mm Pier with 34% and gray color represents 30 mm Pier with 39%. Therefore, it means there is a 12% difference from slender Pier to thicker Pier due to the obstruction. Figure 12. Percentage about distance downflow vortex relation. It is shown for Figure 13, 14, and 15 at 0.117 m/s speed, then Figure 16, 17 and 18 at 0.163 m/s speed corresponding to downstream area, How flow water vorticity was generated due to the different pier thickness, started from hitting the bottom up to be next the pier. Arrowed line leads each horizontal distance from vortex to pier. It is shown in figure 19, a top 20 mm pier view accomplishing observe the von Karman vortices at 0.117 m/s speed. It is shown in table 2 and table 3, downstream flow vortex and its position due to pier thickness for each corresponding speed. 500 equals Re equals 2000. Pier. The data from table 2 and table 3 is arranged to create a king of experimental nomogram shown in figure 20, using at least 2 points water flow speed, y speed, m/s, and 10 mm, blue line, 20 mm, red line, to 30 mm, gray line, pier thickness for obtaining in horizontal vorticity distance, x position, mm. Conclusions. Using Lavizi and DAVIS8 video software processing and post-processing with TechPlot 360 software, it was possible to obtain images of the study areas in 2 dimensions, flow profiles. In the upstream study area location, the flow through the slimmer pier showed a linear trend behavior, generating a moderate small vortex, and for next 2 piers, the flow tended to hit the bottom, increasing its vorticity and going further back a long distance at different positions. In the downstream study area location, the flow became increasingly abrupt as the pier thickness increased, observed by the number of vortices and vectors direction, until hitting against the pier. It is evident that the relationship is directly proportional: the bigger the thickness, the bigger the turbulence, and therefore a bigger scour probability. Analysis of variances for each pier indicates an important significant difference, but also from point of view of water flow visualization at images, it is possible to see. Hence, the importance of building a slender pier as possible, where water flow passes by.